Alright, so for today we'll be doing dimension analysis. Now, imagine you're a guy, and if you are a guy, stop imagining, because, well, you are. And then there's this really, really nice girl that you're totally into, and then you later find out that she's also into you, and you're like, what the hell? That's so crazy. But then here comes the realization that you and her actually might be related. You know, you might be brothers or sisters, and that's simply sad because, you're related. Yeah. Yeah, so this is what happens in the world of physical quantities, where we get one physical quantity, and then we try and marry it off to a bunch of physical quantities this side. Now, before we do that, we must check the type of relationship that they have with each of them. Yeah, we must check the type of relationship. Now, checking the type of relationship, this is where now we're going to introduce our own powers. So let's say x, y, and z at a certain point. Yeah, we're going to introduce our certain powers. Now, these powers are going to tell us what type of relationship these physical quantities have with this guy here. If it is a direct relationship, then you're going to have a positive power. Positive power, which can be any number. It can be a fraction, it can be a whole number. And then we can also think of an inverse type of relationship where it's going to have a negative power. A negative power simply means it is going to go below as a denominator, yeah, and that is inverse. So an example of an equation that has a direct relationship with these physical quantities is this one here. So you get to see that mass is directly proportional to the force. Acceleration is directly proportional to the force. So if mass increases, force increases. If acceleration increases, force also increases. But when we look at something like pressure, which is equal to force over area, we're going to see that, well, force is directly proportional to the pressure, but area is inversely proportional to the pressure. This simply means that if force increases, then pressure will also increase. Yeah? But if area increases, pressure is going to decrease. So that's an inverse type of relationship. So we get to see this and all that under the dimension analysis, where we're going to derive different types of equations and relationships. Now, note that dimension analysis can be used in many different areas, but the main three are one, the same one, deriving an equation. I don't know if that's how you spell deriving, but yeah, deriving an equation. And then the other one can be checking if an equation is correct or consistent. Yeah. And the last one is deriving dimensions of a physical quantity. Yeah, of a physical quantity or a constant. Deriving dimensions. So those are basically the main uses of dimension analysis, and these are the ones that are mostly examined on. So for today, we're only going to look at this one. This is deriving equations, or luckily they're not related, and they can be married off. So remember what we said. When we have a physical quantity, we relate it to other physical quantities. Now, to know what type of relationship, we're going to introduce powers of our own. So that can be x, y, and z, or it can be a, b, and c. It can be anything. Yeah. So something that separates the bride to the groom in these dimensions. So you can say this is the bride, and then all these other guys here are the brooms, or the grooms at the brooms, the grooms. So this can be like acceleration, this can be radius, this can be maybe velocity. Yeah. So the thing that sort of separates this guy from this guy in your question is the word depends. Always look for this word. Alright, so you can be dozing off as you're reading through the sentence, but when you look at this word depends, your mind must be awake, and you must start scribbling up something, because when they say density depends on, so you must write, alright, my density depends on blah 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 blah. And then you're forming an equation. When you look at your variations, you're going to introduce a constant k with your blah 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 constant somewhere that side. Now, enough of the blah blah blah. Let's look at something practical. Let's look at a question. Yeah. So this question says, number one says, what are the three limitations of dimension analysis? This can be what? Number one, dimension analysis cannot help you to find the exact value of a constant. Yeah. Because remember, when we say distance depends. When we say distance depends on the radius, the velocity, and the acceleration, our equation is going to be d is equal to, we introduce a constant k, and then r VA. Now, to know what type of relationship they have, we're going to introduce powers A, B, and C, and then you have to solve for that A, B, and C. But this constant K just remains K because dimension analysis cannot help us to find the exact value of that K. Yeah, so that's one limitation of dimension analysis, and I'm sure you'll find the rest of the two, but yeah, that's the first one. Yeah, so to the deriving equations ones, which is the second one, that says, assuming that the mass M of the big stone can be moved by the flowing river, it depends. Oh, interesting. Yeah, you've seen that, right? This guy here. So, assuming that the mass M of a big stone that can be moved by flowing river depends on velocity v, density rho, and what? Gravity g, acceleration due to gravity. Use dimension analysis to find the expression of M. Yeah. So here, what is our keyword again? Depends. What depends on what? Mass depends on velocity, density, and acceleration due to gravity. Yeah. So let us write this here. Cool. So we have this thing where we have this depends on all that. Now let us formulate an equation from what we've been given. So we've been told that mass depends on all these guys. Now I would prefer my mass to be a small letter m because that is how physics prefers mass to be. So I'm going to write like that. So from an equation, I'm going to say m is equal to, at this point I'm going to introduce a constant k, and then I'm going to have the velocity. The density, they used the symbol rho, so I'll respect that, and then gravitational acceleration, g. Yeah, and then what do I do here? To know what type of relationship these quantities have with the mass, I'm going to deduce what? My powers. So these powers can be x, y, or z. These powers can also be a, b, and c. It depends. It can be anything. Yeah, so we have that. So let me put a, b, and c there. Right, and then at this point here, I'm going to keep this expression. I'm going to bank this expression because I'm going to use it later on after I find my values of A, B, and C. So to find my values of A, B, and C, I'm going to deduce dimensions for each and every physical quantity here. So I'm going to start with what? Mass. What are the dimensions of mass? That is just capital letter M, yeah? Dimensions of K. K is a constant, and constants don't have dimensions, so I can just ignore that for now. Dimensions of velocity, it is LT negative 1. That is to the power what? To the power of A. Yeah, and then what else do I have? I also have density. Now density is ml negative 3 to the power of what? To the power of b. And then my last one is gravitation acceleration, and gravitation acceleration is lt negative 2 to the power of something c. Yeah, so I have that. Now let me try and expand what I have on the right side of the equation. So I'm going to say this. I'm going to say my mass m is equal to, here distributing the a with both the l and the t negative 1 is going to be l a t negative a, right? And then distributing my b to m and l to the power of negative 3 is going to be m b and then l negative 3 b. And then distributing my my c there, my power of c, to the l and l to the power negative 2 is going to give me l to the power c and l negative 2 c, like that. Looks good, yeah. So I'm going to continue on by simply grouping those with the same bases, yeah, like with the same letters. So here I'm going to have my m's remains, but check, I have L, L, and L. So looking at the fact that they have the same basis, I can combine them where I can add the powers, since I'm multiplying L times L times L times this L, right? Yeah. Wait, this is supposed to be T. This is supposed to be a T here. My bad. This is supposed to be a T. Wait, no, crap. Supposed to be L and then a T there. Lovely. Now it looks lovely. Yeah, now it looks lovely. Anything else? No, nothing else. I think this is it. I think we're good to go. We are good to go. Let's look at the question. There's velocity, density, and acceleration. Velocity, the density, and acceleration. Yeah, that's good enough. That's good enough. So let's roll. Let's roll. So from here, I'm going to have what? I'm going to have my 1L, and then I'm going to add up the powers. So it's going to be A minus 3B plus C. Okay, so that's my L. And then I'm going to have my T here, where I have negative A. And then I have negative 2C, yeah? Then I have my M, which is to the power of B. And it's only one M, so I'm just going to write it like that. Yeah, so now reaching at this point here, I need to equate physical quantities here with the physical quantities here. Now notice that on the left side here, I only have M. Now, physics allows me to introduce the L and the T, but they'll all be to the power of 0, since anything to the power of 0 is, just nothing. So I can write it as that. So looking at this, you can look at it in this way. So here we have L to the power 0 and T to the power 0 as well. So equating them one by one, I'm going to start with my M. So M, this one here, is equal to M to the power B, which is that one there. So cancelling out my bases, I'm going to manipulate my powers. So this one has a power of 1, so I'm going to manipulate 1 is equal to B, so B is equal to 1 there. So I have successfully found one letter, so I need to find all the other letters. So after finding B, I can simplify out this one here. What I'm going to have, let's see, I'm going to have my L to the power 0 being equated to my L to the power of A minus 3B plus C. So this is going to be 0 is equal to A minus 3. I have found B, which is 1, and then plus C like that. So this is going to be 0 is equal to A minus 3 plus C. So A plus C is equal to positive 3 if that 3 crosses the side. So I have this. But then I also have this other guy here who says what? This guy says that t to the power 0 is equal to t negative a minus 2c minus 2c. So it's going to be 0 is equal to negative a minus 2c like that. So positive a is equal to negative 2c. Yeah, looks good. So I can get this positive a, and then I can replace it in this equation here. Alright, so I'm going to say replacing it is going to give me negative 2c plus c is equal to 3. Now this is going to give me what? This is going to give me, if I bring this here, it's going to give me negative c is equal to 3. Therefore, I can conclude to say my c is equal to negative 3. Is that good? That's right? Yeah, so I have that. So my c is equal to negative 3. So what else am I remaining with to find? B. So I have found A, I have found C. Now let me find B as well. So how does my B go? I have found B, so I need to find A. So at this expression here, we noted that A is equal to this, yeah, and then I've noted that A is equal to 2. My C is negative 3 like that, so A is equal to positive 6. Yeah, that looks good. So I found my A, my B, and my C. Yeah, I have found my A. To be 6, my B to be 1, and my C to be negative 3. So let me get rid of all of this. So remember this expression that said M is equal to K, and then I had V, and then I had this, and then I had this. Now remember that they had powers A, B, and C. So at this point I'm going to say M is equal to K, V. What was my A? My A was 6. What was my B? My B was what? 1. What was my G? My G was negative 3. Yeah. So it's going to be M is equal to K, V to the power 6, that there, and then changing this to a positive power is going to just be this. Yeah, so meaning this is my expression for mass given those conditions. So yeah, then that's your 9 marks there. Pretty neat, huh? Yeah.